Now to introduce Dr. Jennifer Wiseman, who is Senior Project Scientist for NASA's Hubble Space Telescope and was formerly head of the laboratory for exoplanets and stellar astrophysics. Well, a PhD student, I think you discovered this comet, which I think is rather fine, I have to say. Comet 114P/Wiseman Skiff. She is very interested in the whole relationship between science and religion, speaks on it frequently, she is the council president of the American Scientific Affiliation, which is equivalent to the UK Christians in Science, and she is the new director of the Dialogue on Science, Ethics and Religion for the American Association for the Advancement of Science.
Great. I'm going to be talking about our place in an amazing universe. So we're going to try to re-gear our thoughts now back to the universe and cosmology and that whole picture, and then how a planet like ours and life on planets like ours might come to be, how we might detect it, and what it might mean if we find it or if we don't find it. So let's start this little journey. I want to give you just a little bit of a refresher on the universe so that you can kind of get the context for what we're talking about. So bear with me for a few minutes as I show you some images of bigger things in the heavens, and then we'll focus in on this whole concept of planets and extrasolar planets. This is a cluster of stars. It's called the Omega Centauri star cluster, and it is a relatively new image from the Hubble Space Telescope. The Hubble telescope is a telescope that's in orbit around the Earth, and because it's above the atmosphere, it can send back very clear images. This one I like. It was just a calibration image that was taken right when the camera was installed on the telescope 3 years ago. But it shows you this enormously beautiful collection of stars. I don't know if it's possible to lower the lights at all, or does that mess up the filming? Or anyway, some of these pictures look even nicer in the dark, but I'll leave that to our audiovisual professionals here. Just a little bit of inspiration here from a couple of great thinkers. A philosopher, Kant, said that two things continued to fill his mind with ever-increasing awe and admiration: the starry heavens above him and the moral law within him. And I find that to be true still today. It is true that looking at the vastness and the intrigues of the heavens, and indeed now also on the small scale, the subatomic scale, studying things at these enormous scales of small and large can give us ever-increasing awe and admiration. And also our sense of justice within us and moral law can also give us a sense of awe, wonder, curiosity, admiration. This is what inspired C.S. Lewis to consider seriously coming to faith in God when he realized that everyone has some sense of justice within them. Where does that come from? And then John Calvin, theologian, said back in the 16th century that astronomy is not only pleasant, but it's also useful to be known. It cannot be denied that this art unfolds the admirable wisdom of God. So looking in the heavens can tell us something about God. Is the darkness here going to affect the film?
I think we're okay.
Okay, all right. So just a little background here. The universe, I want you to know, if you haven't noticed already, is beautiful. It's very hard to see it from Cambridge because it's always cloudy. But if you can go to a nice place that's clear and dark, which is very hard to find on this planet now, you can look up and see great beauty. This is an image of a region of the sky known as the Orion region. And this is a picture taken from a nice telescope on the ground, but you can see the famous constellation with the bright star Betelgeuse at the top and the bright blue star Rigel at the bottom. And in this square box region in the middle, if you look closely at the stars therein, you see that they look kind of fuzzy. And astronomers call fuzzy things, we call them nebulae. So there are several nebulae in this region. If you hone in on the one toward the bottom of that box with the Hubble Space Telescope, you see something like this, which is this beautiful swirl of gas and dust. This is a region where stars are still forming. So when stars form, and stars simply form when there's a pocket of gas that's over dense relative to the turbulence of the region, gravity can cause that clump of gas to collapse in on itself, and the pressure within can cause the hydrogen, of which most of this gas is composed, to fuse, and in that whole process, hydrogen atoms fusing together to form helium releases photons of light that then ionize the surrounding gas, and we see it as beautiful colors. So the Orion Nebula is not only beautiful, but it's a very active hot pot of star formation, and in fact behind this lit up region is a much larger, dark, dense cloud where there are young proto-stars that have not yet turned on, but they're in the process of forming. That's what I studied for my own research. These nebulae and stars together make up large collections that we call galaxies. Galaxies are collections of hundreds of billions of stars, and the gas and dust that comes between them. They're held together as a whole by gravity, and over time they can take on these beautiful shapes of spirals such as this one. And in the background of this picture you see other galaxies here and here and here and here and up there. This is just what I call an enormously beautifully symmetric object in space. We believe that we live in a galaxy like this. We can't get outside of it to take a picture, but our Milky Way galaxy is a spiral, and we believe that our sun is a star about 2/3 of the way out from the core of our own galaxy, and we can tell that just by looking around in the sky different directions from our own position in space. The whiteness in the middle here is due to the starlight kind of all blending together in the core where there are so many stars. We use technology to help us understand the heavens. So astronomy is one of those many fields of science where the development of technology is helping to give us a better window of our place as humans in the cosmos. And then that can also feed into our thoughts of theology and philosophy, this kind of thing. It all works together. This piece of technology is the Hubble Space Telescope. It's about the size of a bus, and it's in continual orbit around the Earth. It makes a complete orbit every 90 minutes, and it's constantly sending back images and data for scientists to look at. Our technology in terms of telescopes has improved drastically over the last few centuries. So in this particular chart, the timeline of the last few centuries is seen here on the bottom. And on the side axis here, you see the improvement in sensitivity of images over what you could see by just looking at the sky with your bare eyes. And so each one of these tick marks is 10 times more sensitive than the one before. It's a logarithmic scale. So you can see that starting with Galileo, who was the first person to actually record astronomical observations with a telescope, through the centuries, the growing of eyepieces and telescope sizes, you see this enormous improvement. And then what really changed things was when we were able to record the light in photographs, because then you could observe things that you would never even see with your naked eye. You could collect light for many hours or many days and see faint things, distant galaxies and so forth. This led to a great debate as to whether these fuzzy things on the images were actually outside of our own galaxy, whether there were in fact other galaxies. And so we've only known for just within the last century that in fact there are other galaxies outside of our own Milky Way. And then with the development of electronic recording, that precision got even better. Then we sent telescopes to space. The Hubble Space Telescope gave us 2 orders of magnitude improvement just because we could get above the atmosphere. The atmosphere blurs our images a little bit, so getting a telescope out into space improved things. And this telescope has been serviced by astronauts several times. Astronauts will go up on the space shuttle, dock with the Hubble Space Telescope, put in new instruments, repair things, so we could continually improve the telescope. And in fact, we've done that 5 times over the last 22 years. So the last time we called Servicing Mission 4, even though it was the 5th servicing mission, we went off the charts here. So the sensitivity of the telescope is fantastic right now. And we will not be able to service it anymore because the space shuttle program has been closed. And so we have a very good telescope right now, but we're hoping it will work at least a few more years before we need a new telescope. And there's a new one being developed, so it should be okay. There's our happy astronauts from 3 years ago. I was a part of that process of getting the telescope serviced. It was very exciting. We worked very hard for years to get this servicing mission planned. They went up into space for 5 days. They worked on the telescope, pulling out old instruments, putting in new ones. Engineers, managers, news reporters, all worked together as a team to make this a success. And there were some days when it was very tense. They couldn't get a bolt to come loose, or they had problems getting into the instruments. And there was at least one person praying in the control room for deliverance. That would be this person. And thankfully the mission came out very successful, and now we are reaping the scientific benefits of this fabulous piece of technology. So one of the new cameras, the Wide Field Camera 3 as it's called, starts to give us these beautiful images. And we can see here the vast array of different colors of stars, even in this one cluster, everything from reds to blues to greens to whites. The red stars actually are the ones with the cooler atmospheres. The blue stars have the warmer, the hotter atmospheres. And most stars are these kind of white color in between, such as our own sun. I think it looks like a collection of gemstones, so I think beauty is apparent there. Where do these clusters sit? Well, this is a picture from the ground, and we're going to zoom in to this particular star cluster and get closer and closer in so that we then hone in to what the Hubble Space Telescope can see. So as we go closer and closer, we just transitioned into our Hubble image. So I wanted you to see the larger context of where that is. Anybody feel the heat?
Can we see that again?
Yes. Can we see that again?
You want to see it again?
Yeah.
All right. Ready? Okay. So from this, I also want you to get the sense that there are a lot of stars.
Really?
So I can tell you the numbers, but I think it works much better with pictures. There are hundreds of billions of stars just in our own galaxy, and in clusters and outside of clusters like this. And then now we know there are hundreds of billions of other galaxies. So the universe is enormous, both in the numbers of stars and galaxies, and in the size and in its age as well. The other point that I want to set as the stage here is that our universe is active. It's not stagnant. Many times we talk about the heavens and the earth, and even the biblical texts talk about the creation of all the stars as though it was a one-time event and that they're just sitting there. But in fact, we live in a very active universe. Let's do another zoom in here. This is another picture from the ground, and we're going to zoom in to what the Hubble Space Telescope can see in the core of this nebula, another collection of gas and stars. And as we zoom into this one, we'll see what the Hubble Space Telescope can see as we zoom into very high precision here. So as we get down in this cloud, as in many other clouds, we see these columns of very dense gas. And then something happens. What just happened there? Okay, so we zoom in, and it turns out that these dense columns of gas, which are common in these interstellar clouds, are invisible to regular telescopes because they're full of dust. They block the light. You just see the columns. But some telescopes, like the new camera on Hubble, have infrared capabilities that allow you to kind of see inside. So in this case, the optical light camera here shows you the column, and you see some interesting hints of some things going on there. But it's in these densest regions that new stars are still forming. That's where the gas is the densest. And so by looking in the infrared colors, you can actually see a baby star bright in infrared light because it's hot. We call it a protostar that's on the process of forming. And these funny looking jets coming out of it are a common stage. As stars form, material's falling in on the star, but some of it gets caught up in magnetic fields around the star and actually get ejected out the poles of the protostar. So you see these bipolar, sometimes twisted jets as you do in this case. So the universe is still actively forming stars. Our new technologies allow us to see that. Some of these young stars, this is back in the Orion Nebula, some of these young stars, as you look closely at them, they show these flattened dark disks around these protostars as we see zooming into these objects in Orion. It turns out that these dusty disks are common features of young stars when they've just formed or as they're forming. And these are about the size of our solar system, or a little bit larger. It turns out that these are the regions where planets form. And then just to remind you, on the other end of a star's life, stars burn, but they don't burn forever. And when they run out of internal hydrogen, they become unstable. The largest stars will explode. You saw this picture yesterday. The Crab Nebula is the remnant of an exploded star from 1,000 years ago, and we're still observing that remnant today. The stars themselves produce heavier elements, and these explosions will disperse those heavier elements into interstellar space, and they feed into the next generation of stars, creating things we need for planets. Galaxies actually can merge together if the gravitational pull between them is strong enough. Here are two galaxies being drawn together. Most galaxies are moving apart from each other because of the expansion of space. But if there are two that are close enough, their mutual gravity will become the dominant force. They will be drawn together. That process can start out gently like this one, but the mutual tidal forces and gravity can create a lot of turmoil and turbulence. Here's a couple of galaxies a little farther along in this process. The merging process has created so much turbulence that it has spawned a lot of active star formation, which is what those bright spots are. This will eventually end up as one merged galaxy and a lot of new stars. And just so you're not too comfortable, it appears that our own galaxy, the Milky Way, is heading for a straight-on collision with the Andromeda galaxy. And so our two galaxies will be performing the same energetic dance in about 4 billion years. So we have that to look forward to. Generally galaxies, these are galaxies. Each one of these spots of light are hundreds of billions of stars. And each one of these, for the most part, are being pulled apart from each other by the expansion of space. All right, so that was just your general cosmology overview. Now I want to get back into our own galaxy, and again, we can't take a picture of it. I'm going to skip that right now. Our own galaxy, we think, looks like something like this. We're going to hone into the region around one star, our own sun, which is somewhere out in one of the spiral arms. And what we're doing now is looking at our neighboring stars, stars around our own star, within our own galaxy, and we're starting to discover that there are planets around other stars. So let's try to think a little bit about our own planet Earth and other planets and how it fits into this cosmos. There are about 200 billion stars in our own Milky Way galaxy. So this is a picture from a ground-based telescope of this core of our galaxy, part of it. And you can see this lane of dust that sits toward the center of our galaxy. And all of these stars, the stars are very dense toward the core of our galaxy. Gives you a sense of the numbers of stars. One of these stars in our galaxy is our sun. And so the question has been asked over and over, why would our star be the only one that would have planets? Is it the only one that has planets? And if so, why would that be the case? But we've never been able to answer that question for sure until the last decade or two, when the technology has gotten good enough to be able to detect the presence of planets around other stars. This is helping us to address the age-old question, are there other planets in the universe, like Earth, Is there another Earth out there? And of course, what we'd like to know is there other life out there as well? We don't know the answer to that question. This speculation has been going on for as long as people have looked up into the sky. And in fact, even the ancient Greek philosophers thought about there being other worlds. Now, they may have used that word world in a way that is different than how we use it. But Epicurus even said there are infinite worlds, both like and unlike this world of ours. We must believe that in all worlds there are living creatures and planets and other things we see in this world. So the imagination was going strong for many, many centuries. Medieval scholars also had some of the same thoughts. Giordano Bruno said that there are countless suns and countless Earths all rotating around their suns. See, this was a pretty modern thing to say because he's only speaking there in the 16th century. Countless Earths all rotating around their suns in exactly the same way as the 7 planets that they know then of our system. The countless worlds in the universe are no worse and no less inhabited than our Earth. Pretty imaginative, pretty bold statements. He did get burned at the stake, but I don't think it was. I don't think it was for this statement. Okay, so what about planet discoveries in our own solar system? Let's start with that first. We have our sun. Of course, for as long as we have human history, we've known about these wandering stars in the sky that aren't really stars at all. Mercury, Venus, of course, Earth, Mars, Jupiter, and Saturn. And then Galileo understood that Jupiter itself has orbiting bodies around it, and that transformed our understanding of the dynamics of the solar system. And then we found moons of Saturn back in the 17th century, Uranus, Neptune, and then Pluto was discovered back in the 20th century. Pluto, by the way, was not deemed a planet at first. It was only thought of as a planet a little bit later, and now it's thought of as a dwarf planet because it turns out there are a lot of these small rocky objects out where Pluto is. And now we know of hundreds of not just planets, but moons, dwarf planets, asteroids, things we call minor planets in our own solar system. Extrasolar planets are planets outside of our solar system. So this has been something that has been contemplated, thought about for such a long time in astronomy, but we didn't have the technology to find it. Exoplanets means just what it sounds like. The exo means outside, planets means planets. So planets outside our own solar system. They're sometimes called extrasolar planets. And they were discovered at the beginning of the 1990s, actually, or right at the end. There was some sputtering, as there is at first with new scientific discoveries. There was a report of the first detection, and then it had to be retracted, and then there was another detection. But this whole, these people were very energetic astronomers who were brave to find these first evidences of planets. The first ones being found around odd stars. We call them pulsars. These are old, basically dead stars, but they are easy to track their motion. And how these planets were discovered was not by taking a picture of them, but by noticing that these stars wobbled in the sky. They moved periodically toward us and away from us. And by very careful monitoring of this wobble of these stars, you could tell what must be tugging on them, what body must be orbiting them to create that mutual gravitational tug, to create that vision of a star wobbling in the sky. If you could leave our solar system and look back and measure our sun very carefully, you would see that our sun is wobbling in the sky due to the motions and the mutual attraction of all the planets that are orbiting our sun. The same is true for other stars that have planets around them. The most famous team of planet finders is Jeff Marcy and Paul Butler. Let me see if I got a picture of them. These guys here, they perfected this technique of looking for stellar wobble and found hundreds of systems that have planets around them this way. So how do we detect these planets? We have to be like detectives. It's very hard to find a planet, which is a very small, dim object, near a very bright object, which is a star. And planets don't shine their own visible light. They only reflect visible light. So they're not easy to find. But again, there are intriguing, I would say very creative techniques that have been developed to find these planets. One is, as I mentioned, look for tugging motions on the star. Doppler shifts, meaning that the frequency of the light that you receive from a star is slightly shifted, either higher in frequency or lower in frequency because of this motion of the star back and forth. Or if it's moving in the plane of the sky, you can actually track the absolute position of the star as it wobbles around. There are other techniques which I'll show you a little bit more of, which is to look for starlight look for the starlight dimming. If a planet orbits along your line of sight in front of the star, every time that planet goes in front of the star, between you and the star, the total amount of light you receive is going to be diminished. Or what you'd really like to do is take a picture, image the exoplanet, but as I mentioned, that's very difficult because you have to suppress the bright starlight in order to see the extrasolar planet. Most of this work has actually been done by telescopes on the ground that were designed for this kind of work, or at least the telescopes are facilitated for this kind of work, and powerful computers. Here's an example of how this radial velocity or this wobbling detection is looked at. The scientist looks at the star. The star has to be a happy star. It has to be smiling. And receives a certain wavelength of light when the star is in the moving away from you part of its wobble. And then as it moves towards you, the light that you receive it at a bit of a higher frequency than it was emitted because of the relative motion of the star and the receiver. And as this happens periodically, you can record that. What that really looks like is taking a spectrograph and spreading the light from particular elements of the star into its constituent frequencies, usually hydrogen. Hydrogen has a certain pattern of frequencies at which it emits light, and you can see how that pattern shifts in frequency back and forth. And so astronomers measure that with a spectrograph, and they can detect, it's pretty straightforward, what type of planet might be orbiting to create that kind of shift without even seeing the planet. You can also measure the star as it's moving relative to other stars in the sky. That's called astrometry. And there are telescopes being designed to do that much more precisely from space. That's what it looks like when you measure the motion of the star in the sky over time. And again, you can infer from that the mass of the planet or planets that's causing that tug. And then the third way that is sort of the main future goal, and it's done a little bit now, is to actually take an image, a picture of the planet, because if you can isolate the star and planet, you can study the planet separately. And you can take a picture, and you can take a spectrum of it, which means you can take the light from the planet itself, or that's reflected off the planet itself, and divide it into its constituent colors with something like a prism, and then you can study what it's made of, the atmospheric composition. And so this is something that future telescopes we're hoping to be able to do better. Block out the starlight, and suddenly you can see the planet better. All right. Now, most of these planets, we've detected hundreds of them for sure, and thousands of candidates of potential planets outside our solar system. Most of them are these big gas giant planets like Jupiter, because they're the ones that are easier to detect. They are bigger, they have a larger effect, they're easier to find. But of course, what we're all curious to know is if there are things as small as Earth around other stars. The problem, as I mentioned, of taking images is that stars are a billion times brighter than the planets we're looking for, and so it's like looking for a firefly next to a lighthouse. So you have something this bright, and then you have your little firefly up here, and there's actually one flying around. And so how do you block out something that's that bright to see something that's dim? This is a problem in technology, and it will be solved, but it's a matter of time and budget. So here's our firefly hidden in the glare. We're already doing a little bit of this for certain systems that it's possible. This is a star system called HR 8799. In this system, the planets were far enough away from their parent star and big enough that we could actually use the coronagraph, we call it, to block out the starlight. This is from the Gemini Observatory, an observatory on the ground, and isolate 3 planets that are around this star. So these planets are big gas giant planets, but nevertheless it shows you that we're making progress in actually imaging planets around other stars. Another very popular and fruitful technique is called transits, and that's when the planet happens to orbit in front of its parent star, so that the total amount of starlight you see drops when the planet is eclipsing part of the star, and then it jumps back up again. You may not be able to see the planet, but you can see the amount of starlight that's fluctuating, and there's a lot of information you can get by looking for transits. NASA has a telescope in space right now that's looking only for transits. It's called the Kepler Space Observatory. And Kepler has been up in space for 3 years now, looking at a collection of 100,000 stars, just staring at them, and trying to find out how many of them have these periodic dips in their brightness, and how many of them we can infer have planets and what kind of planets are surrounding them. Here is if this works, yeah, this is what a transit looks like, okay? A planet going in front of its parent star. This is an artist's conception here. But you see the total amount of light dipping as the planet goes in front. Now what's also very interesting is the starlight comes through these surrounding edges of the atmosphere of that planet. You can do spectroscopic analysis of what's absorbed by that planet's atmosphere, and that tells you something about the composition of that planet's atmosphere. So this is an artist's picture of this Kepler telescope that's out in space right now looking at this. These are the first few planets that Kepler detected back in 2009. And of course the first ones it detected were the ones that had the fastest orbits, because it could quickly detect a drop in light regularly for these objects. So you see these dips in light. The total amount of light would be steady and then dip when the planet goes in front of it. These first planets had orbits that took the planet around the star in just a few days, 3 days, 4 days, 5 days. Our Earth takes 365 days to go around our parent star. So these are very close to their parent star. We call them hot Jupiters because they're so close to their star, they're very hot, and they're big like Jupiter. But this was exciting to actually see, to start actually detecting the transits of planets around other stars. There's a fourth way, which I won't discuss too much today, but the evidence for planets can also be found by looking at the disks of dust and rocks that surround stars. I told you that many stars we're finding are surrounded by these dusty disks. Here's an example. This is a ring disk around a star known as Fomalhaut. The Fomalhaut star has been blocked out by a coronagraph on the Hubble Space Telescope here. That radial noise is just that, it's noise from the coronagraph. But the ring structure there is actually real, and that sharp ring is shaped by the presence of at least one planet in this system. An object buried near this ring was detected in old data from images in 2004, 2006 that appears to be moving, and there's some speculation that this might in fact be the planet that's shaping the ring. There's some controversy about whether or not that's the case. But there are several systems now where we can see evidence of planets in the dusty rings around stars. All right, so what's happened? You live in a very exciting time, because you see 20 years ago or so, all of this discussion of planets around other stars was science fiction. And over the last 20 years, it's turned from science fiction into science fact. We started back in the early 90s just detecting 1s and 2s and 3s every year, but as these techniques got better and better, the number of planets detected every year has gone higher and higher. This goes up to May of 2012. So by the end of this year, the number will be far, far higher than the year before. So you see this exponential increase in the number of discoveries of extrasolar planets just in the last few years. And it's because of the development of these techniques and new telescopes. All right. What do these look like? So the Kepler telescope, by the way, I should just mention, Zoe, it doesn't appear that the power is actually coming to this thing, so I hope my battery will last. Anyway, the sizes of these things, which you can tell through transits, are in many ways a huge variety. They're huge. This is the size of planet Earth, and these are the first few planets detected by Kepler, and most of them are much larger than planet Earth because they're the easiest ones to detect. As of February of this year, they had enough detections, or candidate detections. I told you there were a few hundred detections. Those are confirmed, meaning they were detected with Kepler, and then follow-up studies looking for wobbles in the parent star confirmed there were planets there. But there are many more candidates that have yet to be confirmed. There are over 2,000 candidates now, so you can start to do statistics of planets. And it turns out that in this collection so far, Kepler has found over 1,000 Neptune-sized planets, 200 or so Jupiter-sized planets, and then a few hundred that are a little bit larger than Earth, and maybe at least 200 that are Earth-sized or smaller. So you can start to get a distribution to see what kind of planets are most common. It turns out that planets the size of Neptune are the most common, and Jupiter's are less common, and Earth-sized planets, there are some. As you get smaller and smaller, they are less common. It's amazing that we can do these kinds of statistics now. You can see how this has changed just in the last couple of years. As of June 2010, the blue dots here tell us the planets that have been found. This is the size in terms of radius relative to the Earth on this axis over here. And so in 2010, we had only got down to a few sizes larger than Earth. By February of this year, we've actually found some that are smaller than Earth. In this chart, what it's showing you is the temperature of the inferred temperature of this planet based on its distance from its parent star. And so the temperatures can get very hot for these planets that are very close to their parent star. But there is a lane in green there that are habitable temperatures, meaning that you can have liquid water that's not frozen and not boiled away. And there are some planets that are in that habitable zone. You see planet Earth there is just the right temperature and just the right size. So we want to know if there are other planets like Earth. And we're getting some data in that regime now of planets that are in the habitable zone and close to being the size of planet Earth. I think I'm going to skip that. We've also seen a planetary system that has multiple planets. This is called Kepler 11, and they found that 6 planets in this system orbited in orbits tighter than Mercury, and you can actually measure something crude about their densities based on their masses and sizes. In this case, very crudely, you can tell that these must be fairly low-density objects, and in fact, some of them seem to have large radii compared to their masses, so they must be mostly hydrogen, helium, things that are not quite like Earth. The fact that you can do these crude compositional analysis with this kind of data is also amazing. This discovery made the cover of Nature, so this is a hot topic. Kepler discovered a planet that's orbiting a binary star system. So now we have evidence of unusual star systems. They call this the Tatooine. If any of you have ever watched Star Wars, and there's this famous scene where Luke Skywalker is standing on his home planet of Tatooine, and there's a double sunset off in the distance. So now we're not just counting planets, we're also beginning to characterize these planets, though very crudely, to find out their mass, density, orbits, and so forth. As I mentioned to you before, if a planet transits in front of its star, that the starlight can go through the planet's atmosphere, we can see it spread it out with a spectrograph, find out the composition of those planets. The first one we did this on with the Hubble Space Telescope, we found out that this large Jupiter planet had sodium, carbon, hydrogen, and oxygen in the atmosphere. We found another planet that, based on the timing of the transit in different wavelengths of light, you could tell that it had a hot atmosphere because the ultraviolet transit started sooner than the visible light transit. This is an artist's conception telling us that this planet probably is so close that it's to its parent star that its atmosphere is being drained off of the planet. Just a week or two ago, we had a press release about an extrasolar planet that occasionally shows high velocity gas escaping from its atmosphere, but it's not constant. What could be causing that? Well, then it turns out that its parent star was having flaring activity that was detected with an X-ray telescope known as SWIFT. And so when you correlated this data together, it turns out that when SWIFT saw an X-ray flare from its parent star, you could correlate that with seeing high velocity gas coming off of the extrasolar planet with Hubble. So you could actually see how a star flare is creating weather changes on an extrasolar planet, and that's quite exciting. Okay. Let's move now for the rest of my talk. I want to talk about moving toward habitability and life and what that might mean for us. So let's talk about that a little bit. Well, as I've been talking about, one of the highest goals is to develop technology that could detect Earth-like planets around Sun-like stars, and to see if we could find signs of life. And for astronomers, that means especially primitive life. We would be very excited if we saw evidence of bacteria or any kind of plant life, anything like that, on another planet. That would be a tremendous victory. Now, from the other direction, there are organizations that are actually listening for intelligent civilization. So they're not so interested in the bacteria, they're interested in the Romulans, or whatever the civilization is. And so the search for extraterrestrial intelligence, which is not a government-funded program, is already listening for signals from intelligent civilization. So we have both ends of the intelligence spectrum being searched for by different groups at this point. Most of the planets that we've found right now are not good candidates for life. I've already mentioned that Earth-like planets are small, they're hard to see, they would need to be in the habitable zone of their parent star. This is not to scale, of course, but this is a picture of our solar system, and most planets, both in our solar system and in other star systems, are not in the right location to be very comfortable for life. We believe life as we know it needs liquid water. Now you can imagine that there might be life forms that don't need liquid water, but we have to start with what we know. And what we know, all life on this planet requires some contact with liquid water to survive. And so the planet cannot be too hot or too cold. Most of the planets are too hot or too cold. They're too far away from their parent star, or they're too close to their parent star to support life. However, we are starting to look at a different kind of star. We call them dwarf stars, or M stars. And in fact, there are a lot more of these small M dwarf stars than there are sun-like stars in our galaxy. So there are many more of them to look at. And it turns out that for those stars, their habitable zone is closer in, because these are smaller stars. So closer into that star is where you would find the liquid water. And a closer in planet is easier to detect by looking for transits. So there are whole astronomy teams now that are focusing on these M dwarf stars, they call them, and looking for transiting systems. And they're starting to find planets that are small, Earth-like planets, around these M dwarf stars, to the point where they can do statistics. They're now claiming that maybe 60% of these dwarf stars have at least one planet in its habitable zone, and many of them might be as small as Earth. So this is quite incredible. This is an artist's conception of one of these systems. It turns out to be a triple star system that has a planet that's the size of just 2 or 3 times the size of the Earth. So we call it a super Earth. And it's in the habitable zone of this star system. And so in this case, you would potentially have the possibility of having liquid water. And that's what this artist has captured here. If these statistics are right, there are likely 65 billion stars in our own galaxy with a habitable super-Earth. Okay? So we've changed in our understanding. How will we know if a planet supports life? Well, we'll look for evidence of oxygen in the atmosphere. Remember, we don't get to go down and take a picture of creatures roaming around on the planet's surface. We get spectroscopy of the atmosphere. So we'll look for evidence of oxygen because, at least on Earth, the only way we get oxygen replenished in the atmosphere is because of life, because of the photosynthesis of plants that regenerates oxygen in the atmosphere. Looking for evidence of liquid water, that doesn't tell you there is life, but it tells you it could support life. Looking for evidence in the entire spectral range of the reflected light that can tell you if there's especially plant life, as we see on this planet. On Earth, animals, especially cows, emit methane, so if we look for some other signs of biological activity on other planets, that can be signs of life. We might find a bovine planet if we see a methane-producing planet, but you have to rule out other explanations for these kinds of spectroscopic signatures. This whole science is called astrobiology, and astrobiology is a new field that's just taking off. It's very exciting. There's only a few types of life forms that create changes in the atmosphere that you could detect from space, so you have to know carefully what you're looking for. In the tree of life, some of these include oxygen-producing organisms like plants. The vegetation as a whole produces a certain cutoff in infrared radiation at a certain wavelength, so you can see that from space as well. There are methane-producing organisms, and so you need to know what kinds of organisms would produce a signature that you can see. You can tell a little bit by just going off of Earth a little bit and looking back at Earth. So this is Earth spectrum from reflected off of the moon, and from this you can see evidence of our oxygen in terms of ozone. You can see evidence of water. You can see scattering from our upper atmosphere. You can see where the chlorophyll affects the spectrum. So you can actually see from the Earth spectrum signs of life, and this is what we would look for in other planets. And of course, you might see a planet that's in a very different age than the Earth is. Earth's atmosphere has not always looked the same. So you have to know what the atmosphere would look like at different time frames. In our planet, we had methanogens and cyanobacteria. They've been around since the Earth was only 1 billion years old. The Earth is now over 4 billion years old. So you have to know what you're looking for. And in fact, over geologic time, the concentration of these different gases in our atmosphere has changed. So over here in our time now, we have a lot of oxygen and very little carbon dioxide and methane, but that hasn't always been the case. So if you looked at a planet, an exoplanet that's at a different stage of development, we might see a different combination of this composition. You need to be aware of that as well. All right, and then of course there is this curiosity about what we would see from intelligent civilizations. I'm not going to go into that, but there's this whole SETI group that's listening for intelligent signals that are intentionally sent from other civilizations. Of course, you have to then, you're imagining what that civilization might be like. And of course, we think of our own civilization and kind of extrapolate, but you have to start somewhere. And I won't go into that, but that's an ongoing effort by certain groups. All right, I'm going to take 10 more minutes because we started 5 minutes late. We've got 5 minutes here. So for the last 10 minutes of this talk, I want to talk about the implications for what would happen if we do or we don't find life. In particular, how would society and different religious traditions respond to the detection or non-detection of extraterrestrial life, whether it's simple life or complex life. We have not detected life yet off planet Earth. Okay, so we're still very interested to know if there's any signs of life, either present or past, on other planets in our own solar system. So far we haven't detected it. Doesn't mean it's not there, it's just that we haven't been able to detect it yet. And we don't yet have the technology fully developed for finding signs of life on other planets. But the key is we're now starting to find these planets and to hone in on this technology. So these questions will become answerable perhaps within our lifetime. Ted Peters, a theologian, did a survey of different religious groups to find out what would happen to their faith and their beliefs if confirmed discovery of an intelligent civilization were found outside our own planet. Would it undercut your beliefs? So he asked people, yes or no, do you agree or disagree that official confirmation of the discovery of a civilization of intelligent being on another planet would so undercut my beliefs that my beliefs would face a crisis? And almost everyone said, no, it wouldn't. Only a few people said yes, only a few people didn't know, they neither agreed nor disagreed. Almost everyone said that it would not create a crisis for their faith. That went for Catholics, Protestants, Orthodox, Mormons, Muslims, Jews. I don't think he didn't have Muslims on this list, but he did survey Muslims as well. Buddhists, non-religious people, they all said, no, it wouldn't cause a crisis. Now, interestingly, when he asked them what they thought about other religious traditions, not their own, will those other traditions face a crisis? And nearly everyone said yes, that other tradition would face a crisis. Now, the thought of there being life on other worlds has been talked about in many religious traditions. In Islam, for example, the Imam al-Razi back in the 12th century said that he, the Most High, has the power to create 1,000 worlds beyond this world, such that each of those worlds would be bigger and more massive than this world. Now again, that use of the word world may be different from our specific use of planets, but nevertheless, this Imam was arguing against the philosophers of his day that said that this world was only one, and he said those arguments are weak and flimsy arguments, that God has the power of creating many worlds. What about Christian theology? Would Christian theology embrace the idea of life on other planets? How about starting with simple life, which is the most likely? If we were to detect life scientifically, really, it's much more likely that we would detect evidence of simple life before we'd ever have the chance of encountering intelligent life. But we need to ask the question for intelligent life as well. Just to remind you, I'm not a theologian, but you need to understand why this question might have some unique issues with Christian theology. Christian theology says a few basic points, and I don't want to get into a theological discussion here, but most Christians believe something along this line, that creation is good, and whatever means it took place, whether God used evolutionary processes or not, it is good, and it is, and God is the author of creation, and that God loves people. God so loved the world that he gave his only begotten Son. That humans reflect God's image, but in some sense we are fallen from that ideal image and that relationship with God, and we need redemption and restoration to peace with God. So that's a key point in much of Christian understanding. We need restoration to be in relationship with God. And there's an additional emphasis in the Catholic tradition of Christianity on original sin that's passed down from the first humans on down to all of us. And that God himself became incarnate, in other words, became human in form to help us, to redeem us, to save us, to restore us. The tradition of substitutionary death is there, that Jesus died to pay the penalty for our sins in human form, and that the whole universe will somehow share in the benefits of this redemptive work that caused by God becoming human. All right? So, how would this apply if we find extraterrestrial life? Now, for most Christian traditions, they can easily extrapolate to extraterrestrial simple life, because if we believe that God's blessings on earth apply in some shape to all life forms here, not just to humans, you could extrapolate that to other life elsewhere. But if it's extraterrestrial life that has a moral sense, or even has a fallenness, such as we have in Christian thought, how would they be affected by Jesus coming in human form? So this is a uniquely Christian dilemma here. Would alien life experience the presence and redemption of God in person as done on earth through Jesus Christ? And how? Would intelligent life elsewhere be so intelligent that they sin like we do? Would Christ appear in various non-human forms elsewhere? Or does his one appearance on earth accomplish redemption everywhere? The Bible says that Jesus Christ is the righteous one, is the atoning sacrifice for our sins, but not only for ours, but also for the sins of the whole world. Does that include the whole universe? Okay, some people think so. Not clear. The Catholic Church that held the Pontifical Academy of Sciences held a conference on this whole topic, including astrobiology, this new science, back in 2009. This is a cartoon from the Washington Post that they may not have thought was all that humorous, but I put it here. But the quote from Father Funes, who directs the Vatican Observatory, who's asked, why is the Vatican involved in astrobiology? And he said that although astrobiology is an emerging field and a developing subject, the questions of life origins and whether life exists elsewhere in the universe are very interesting. They deserve serious consideration. These questions offer many philosophical and theological implications. Two of the leaders there had some quotes about what they thought about finding life elsewhere. Father Denoya said that Christians have always understood that the entire cosmos is a creation of God and that life anywhere is a divine creation. There would be absolutely no motive for scandal if scientists were to establish the existence of life elsewhere. And Father O'Collin said, I don't think the discovery of life on other planets would pose a different challenge than the discovery by Europeans of the new world, which was new to them. It was not new to the natives who were already there. Prior to the 15th century, people, presumably he means Europeans, had only the vaguest idea about human life on the other side of the Atlantic. But we survived that, and in the end, it deepened our understanding of Christ as a truly universal Savior. So the idea here is that if we find life elsewhere, it will deepen our understanding of Christ as a universal Savior. Physicist and philosopher Paul Davies says not so fast. He says, I think that the discovery of a second Genesis, meaning that life started somewhere independently off of Earth, would be of enormous spiritual significance, and that the potential challenge to Christianity is being downplayed by religious leaders. He says the real threat would come from the discovery of intelligence, because if there are beings elsewhere in the universe, these Christians are in a horrible bind. They believe that God came incarnate in the form of Jesus Christ to save humankind, not dolphins or chimpanzees or little green men or on other planets. So there's some disagreement about the impact of this. And so back to our Catholic priests, they do say, well, I guess we do have to think a little bit about the concept of original sin. How can persons on other planets share in the stain of guilt derived from Adam and Eve if they're not descended from them? We'd have to work a little bit, I suppose. But anyone who thinks the doctrine of original sin is more important than Jesus being the universal Savior already has their priorities out of line. In the end, O'Collin says, if there are extraterrestrials, Christians can state with confidence that they too are saved by Christ, even if the question of saved from what will take some reflection. And then quickly, I've got to finish here. What about Protestant views? Most Protestant Christians also see no problem with finding extraterrestrial life, even intelligent life, musing that such a finding would reflect on the greatness and creativity of God. The great evangelist Billy Graham said, I firmly believe there are intelligent beings like us far away in space who worship God, but we have nothing to fear from these people. Like us, they are God's creation. And even C.S. Lewis wrote about his speculations of the spiritual state of possible life elsewhere in his great trilogy that starts with Out of the Silent Planet, a book I just read. I'm going to skip a little bit of this. Finally, we do have to think about how finding life would affect our view of our own significance. What does it mean to be significant? You know, we've now found that we're not in the center of the solar system, we're not in the center of our galaxy is not in the center of the universe. There may be a multiverse. You know, we seem to keep getting diminished in our position in the cosmos. And then if we find life in planets elsewhere, does that further diminish our role? We have to remember that being significant does not necessarily equate to being central or unique. In fact, sometimes rarity does not necessarily correlate with significance. And it turns out that even in Copernican times, being elevated from the center, away from the center, was actually an elevation, not a demotion. That being in the center of things was seen as the worst place you could be. Hell was in the center of planet Earth, so to be outside of the center could be seen as an elevation. And I'm referring to the works of Dennis Danielson, who's a literary scholar at the University of British Columbia, who did this kind of work. So significance is not necessarily based on your uniqueness or your position. Biblically, our significance is based on God's choices. So it's not because of we're told over and over in the Bible that our lives are like lights, glimmers that come and go, that we are like candles in the wind. But it's God's choice to give us significance. In Psalm 103 it says, as a father has compassion on his children, so the Lord has compassion on those who fear him. He knows we are dust. As for man, his days are like grass. But for everlasting to everlasting, the Lord's love is with those who fear or respect him. Praise the Lord, all his works everywhere in his dominion. All right, so most likely our first detection of life will be something simple. And I think we have to reflect on how would such a discovery affect our view of God and creation. And there's no right answer to that. I want to close by telling you some organizations that you might find helpful. The Dialogue on Science, Ethics, and Religion program of the American Association for the Advancement of Science. We try to encourage dialogue between scientists and religious communities on these topics. Of course, the Faraday Institute here. This book, Not Just Science, Questions Where Christian Faith and Natural Science Intersect, is a great study book, and I wrote a chapter in that book. This is a wonderful collection, the Book of the Cosmos, essays from great writers throughout history talking about the cosmos, the universe, and faith, and how they speak to one another. And these organizations I recommend as well, in particular if you're interested in Christian faith and science. Christians in Science here in the UK and the American Scientific Affiliation in the US are helpful organizations for continuing these conversations. You can get my Hubble images from this website, www.hubblesite.org. This is our own home planet. We do know that there's one planet with life, and it's this one. And in fact, when we look back at it from the space shuttle, you see a very thin, fragile atmosphere. And I think one thing we can take from all of this is to know how precious our own planet is, and that we should be good stewards of our own planet, whether or not we're capable of finding life elsewhere. Are we significant? This is my last slide. Carl Sagan, the great astronomer and science expositor, says, who are we? We find that we live on an insignificant planet of a humdrum star lost in a galaxy tucked away in some forgotten corner of a universe. So that's one way you could think of all this, and it is the way some people do. Or you can think of it in a very different way. The psalmist looked up at the skies and the heavens and wrote in Psalm 8, O Lord, our sovereign, how majestic is your name in all the earth. When I look at your heavens, the work of your fingers, and the moon and the stars that you've established, he didn't even know about galaxies and exoplanets. What are human beings that you're mindful of them? What are mortals that you care for them? And that you've made them a little lower than God and crowned them with glory and honor. You've given them dominion over the works of your hands. You've put all things under their feet. So he looked at that same thing and said, aren't we a privileged people to be able to be a part of this universe? And so I'm going to close there. I'm sorry I went over, but thank you for your attention today.
Okay, over to you folks. We've got some time for questions before dinner. Yep.
The stars that you looked at, which you've established as that could be habitable, they're actually not accessible. I mean, they're so far away that we couldn't get to them.
It depends on what you mean by accessible. None of these star systems do we have any way right now of going to, not even with a probe, okay? Because we don't have the technology yet to even send a probe, even to the nearest star to Earth. That's, we are still at this primitive stage of only being able to send probes to planets in our own solar system. So the question, though, is can we do follow-up studies of these that would, at least with telescopes, allow us to do detailed spectroscopy to find out what's in the atmospheres of these planets and to find out if they show signs of life that way. And most of these planets that are being found by the Kepler telescope has given us those statistics of the numbers of Neptunes. They're too far away to do detailed follow-up studies. But some of these studies of these small M-dwarf stars are close enough that we can, with future technology, do follow-up studies of the atmosphere, spectroscopy, and determine whether or not they show what we call biomarkers, which is evidence for life, biological activity. Thank you.
Good, thank you. David, back.
I understand, I realize your argument for keeping astrobiology really terra-centric, if there is such a word, and assuming carbon-based life, assuming oxygen, or things that have happened over the history of the Earth. But inspired, say, by mathematics, which in mathematicians, theoretical minded mathematicians will go in all different areas just to find the possibility space, regardless of whether there are any objects or anything to count in the ways that you can count in math. I was wondering what, just inspired by that idea, are there biophysicists or biochemists that you know of who are looking for other molecules that could harbor microenvironments at various temperatures and pressures, could polymerize at various temperatures and pressures, or replicate, anything like that?
Yes, there are. So it's very, very active field of study to find out what kinds of physical conditions you might get, what kinds of organisms. And in our own planet, there's a lot of study of what we call extremophiles, which is looking for life forms in very harsh places on our planet. The bottoms of the oceans, the pools of acid and things in Yellowstone National Park, other things that are would be thought that carbon-based, water-based life as we know it could not exist. And in fact, we do find carbon-based, water-based life in those harsh environments that have adapted. So extremophiles is one active set of research so that we can know the range of conditions that might be beyond what we had presumed in which carbon-based, water-based life might exist elsewhere. Now you're asking, of course, whether there could be non-carbon-based, non-water-based life. There's been a lot of speculation that there might be silicon-based life forms, but it turns out, and I'm not, this is outside my field of expertise, but the more you look into it in terms of the biochemistry, it turns out that carbon really is the best suited atom for building up complex molecules. And so carbon, there may be better experts in the room, but carbon turns out really does have a unique property that's suitable for building complex life. Now could there, and there are things about building the walls of cells that you need for something you might want to call replicating life, even if it's single cellular, that carbon gives you the unique building blocks for the proteins and things that you need. Now, the other issue is that if you have a life form that's very different from what we are used to, how would you detect it? We have to start with what we know. We know that one kind of life survived and thrived on this planet, and so you have to start somewhere, and you know vaguely how to detect the biomarkers and signatures of life on this planet. What would you look for if you're looking for other things? And then there's the question of what is life? And that question is getting more and more difficult to answer. When I was back in high school, it was very simple. Life was something that could reproduce itself, basically, and now that's not really a satisfying definition of life at all. We have all kinds of replicating systems that aren't alive as we might conceive of it. Even computers can replicate certain things, but that doesn't mean that what they're replicating is alive. So what do you call life? Some define it as some kind of a collection that has a population that has enough variation so that you can get that has variation and the ability to reproduce, so that you can get adaptation to environmental changes, and you might call that life. But you know, what do you call life? That's another whole question of astrobiology. So that's a hard question to answer. Yeah, Dennis might really answer that better than I.
No, I wasn't going to give you the answer to that. I just want to comment on David's question about experts, that that actually another NASA scientist is coming to our next Faraday course, which is about God and genetics in September. This is Stephen Freeland.
Oh, he's wonderful, yeah.
And so, and actually, as it so happens, David is also speaking at that course, so I can do a double plug. So that will cover all bases then. You know,
Good, yeah.
But Stephen Freeland runs a lab to look for chemical constitution of alternative chemical entities that could give rise to life in some way. So different amino acids and so on. So, yeah.
In fact, I met Stephen Freeland through the Faraday Institute. Being here, he was one of the speakers remotely one year, and that's how I found out about him, and I contacted him, and we've become good friends. So thank you, Faraday.
Yes, he was in Hawaii at the time and managed to not leave his passport in Maryland, which wasn't helpful for getting over here, but yes, great. But we did get him, which was great. Yeah, more questions? Yeah.
Jennifer, thank you so much. I enjoyed that immensely. In light of NASA's discontinuation of the Space Shuttle program, which was quite painful to read about initially, I was wondering what your thoughts are on Elon Musk's SpaceX, the Falcon 9 program, and what the privatization of spaceflight means for our sort of ongoing understanding of things. Thanks.
Okay, so what he's talking about is that the Space Shuttle program, which we've relied upon for the Hubble Space Telescope servicing and all of that, is now closed. And so the United States right now doesn't have any way of getting astronauts into space. We use the Russian Soyuz spacecraft to get our astronauts up and down from the International Space Station. So the International Space Station is still in orbit right now. It's a very active and productive facility. And astronauts from many different countries and scientists and researchers are using that facility. But we have no space shuttle. So the impact of that is harsh in the short term, in that we don't have we can't service the Hubble Space Telescope anymore. It will break down over the coming years. I hope we can't predict exactly how many years we have left, but we will lose the telescope at some point. We have another telescope being built, the James Webb Space Telescope, that will be launched later this decade. What's happened is that NASA is actually advocating private industry, as you mentioned, to develop capabilities of bringing cargo and ultimately astronauts into what we call low Earth orbit. So this is the orbit that the International Space Station is on. It's the orbit range of many satellites, of some telescopes like Hubble, so that NASA can concentrate on developing more sophisticated rockets and launch systems that will bring cargo and potentially people to farther distances, maybe back to the moon, maybe to an asteroid, maybe eventually to Mars. So giving private industry the chance, which they've wanted for years, of being able to develop private access to low Earth orbit, and while NASA concentrates on access to farther distances. Conceptually, I think that's a fine idea. That allows private industry to use its ingenuity to develop a more simple way for both scientists and also private companies to have access to their needs in space. While NASA can concentrate on the kinds of things that commercial support would not garner enough funding to do, which is to develop exploration beyond. However, there's always the question of whether or not enough funding will actually be generated to develop those capabilities for the more distant space launches. So I'm waiting to see if this really pans out. Now, as far as the science, such as the Hubble Space Telescope, the other space telescopes, that's a different division of NASA. And while there's never what I would call enough funding to do everything we want to do, we'd like to send lots of probes to Mars and other planets. We'd like to send many space telescopes to look farther out. We do have a healthy program, and that should continue regardless of what happens with the astronaut program. So it's kind of a mixture of astronauts and pure science missions. And right now, as a whole, NASA's pretty healthy. So I think it'll be okay.
Thank you. So any more questions? Yes.
You were making the emphasis on looking for primitive life forms rather than human-like life forms. Presumably because in the whole history of the Earth, the vast majority of that time has been fairly primitive compared to the relatively short time of such as us around. Is there any extrapolation for what this Earth will look like for the next 100 or million years?
Yeah.
Do you know what you would be looking for as a more advanced planet?
That's a really good question. I'm sure there have been some extrapolations, and of course we're changing our own climate even now. So, so what will the Earth's atmosphere look like in the far distant future? I'm not sure. There are people who could answer that question better than I, so I can't really answer that in the far distant future, but that's a terrific question, and I think it's hard to predict. One of the reasons that we believe primitive life is more, well, first of all, even if there were advanced life on another planet, how would you detect them unless they were intentionally sending signals? Well, in some sense, they would produce kind of the same atmospheric compositional changes that we see on our own planet. So you would be looking for evidence of, in some sense, oxygen. In our planet, that's produced by plants, but you could imagine that there could be other intelligent organisms that might have a similar chlorophyll type process. You don't know. So I think it's not entirely differentiated between how you would look for intelligent life versus signs of it, versus biological activity as a whole versus simply primitive life alone. And then there's the issue of the rarity of there's a wonderful book about the chances of us encountering other intelligent civilizations, even if they are there. And the chances are very small, and the reason is that the distances between stars are so vast that the chances of having some sort of meaningful communication is basically almost zero. And also the chances that we've been visited by some alien civilization that has come this far but left really no signs of their existence other than these random late night TV shows that show people being abducted briefly by aliens is also very hard scientifically to believe. There's quite a few reasons to think that life may have trouble evolving to an advanced stage, because as we look to other star systems, it turns out most of them have very thick disks of this dusty debris that I talked about. Well, this debris around stars is what produces asteroids and comets, things that bombard our solar system. We get hit by little asteroids all the time. 24 hours a day, our atmosphere is being bombarded by little pieces of rock. Now, most of this gets burned up in the atmosphere, but every once in a while we get bombarded with a large object, and that can create huge climate change on the planet. It has done this on the Earth in the past. Now imagine you're in a star system where these large objects are much more common. So getting hit with these things is a much more common event that creates huge global climate change. That would make it very difficult to have the stability required for advanced life to evolve and to thrive. So there's some thought that actually having a planet that sits in a system where there's very little leftover debris, such as our own solar system, is an unusual state of affairs, and that most star systems, even if they have Earth-like planets in habitable zones, it might be very difficult for them to have the stability that they need for long-term, intelligent, advanced life to evolve. So that's, we don't know this yet, you know, these are just speculations from looking at the data that we do have. There's one other issue I'll just mention, which is stellar activity. It turns out that the excitement over finding all these Earth-sized, potentially habitable planets around these dwarf stars is muted a little bit by the fact that these dwarf stars are also very active stars. They flare all the time. Well, if you're on a planet that's very close to a constantly flaring star, you are going to get bombarded by cosmic rays and all sorts of damaging radiation and particles that could make it very hard for advanced life to thrive. Now, of course, they could evolve to withstand all of that. So, you know, we just don't know. We need to collect more and more data.